All right, welcome to Teleps in Physics. So now what we're going to talk about today is potential energy, right? So potential energy is energy that's basically stored based on the location of an object. And the type of energy that we're really going to focus in on is gravitational potential energy. But there's other types of potential energy that are that can happen as well. So there's elastic potential energy if it deals with springs. There is electrical potential energy if you're dealing with electric charges that are in an electric field. But we're going to focus in on gravitational potential energy that's resultant of a gravitational field. And so what we're going to look at is we're going to look at a situation where we have a roller coaster that's being pulled up a hill. So we're going to think about the velocity at the beginning and the end as being the same, right? So we're going to have constant velocity pulling it up the hill, constant velocity pulling it up the hill, and we're also going to consider that, basically on a regular roller coaster, it's a motor and a chain that pulls you up the hill. Okay, so it's moving at a constant velocity at the beginning, but it has essentially no height. So what does that mean for our, well, let's actually pick our system first. So we got the roller coaster car, I'll just write it as car, and we have the Earth, right, because it's going up a hill. I think that'll cover it. All right, so is it moving? Yeah, it's moving at a constant velocity. So because it's moving at constant velocity, let's give it some kinetic energy. How much? Let's do 2 boxes. And if it's a constant velocity, it's the same at the beginning and the end. All right, so a constant velocity at the beginning and the end. Now, what about the gravitational potential energy? Well, at the beginning, we'll call it a height of 0, but at the end, it's at the top of the hill. So there's no gravitational potential energy at the beginning, but let's give it some gravitational, let's make it 3. Gravitational potential energy at the end. Now there's no springs, and we're going to consider no friction, so we don't need the other things. So what does this mean? Well, I got 2 bars over here, I got 5 bars over there. So what's happening? Well, I mentioned there is a chain motor system that pulls that up, right? That's doing work. It's from the chain and motor on a typical roller coaster that's going to pull that up. All right. So what does this mean? Well, we're actually going to write this as an equation. And what is this equation? Well, look at the picture. I'm going to have some kinetic energy at the beginning. I'm going to add some work, and that's going to equal the kinetic energy at the end plus the gravitational potential energy. What I'm actually trying to do is figure out what is the gravitational potential energy. How do I calculate that? Well, since it's moving at a constant velocity, this and this, the kinetic energies are the same. So I can say work equals gravitational potential energy. Well, that's a good thing because it turns out we know how to calculate work. Work is force times the distance. And the distance that it refers to is the distance being the height, not how it traveled. It's the height. So this is the distance. It's the height. Because the gravitational field is up and down. Now, in more advanced classes, you'll be able to talk about the dot product of this, which we're not going to do here. So, force times the distance. Well, what force is it? It's the force due to gravity, right? How do you calculate force due to gravity? Well, you calculate force due to gravity as m times g. And then we're going to multiply it by a distance. But more commonly, what you see, the distance is usually referred to as height because we're talking about how high is it. And so this is how you calculate gravitational potential energy. It's the force of gravity times its height. All right. So, for example, what really matters is what's the change. The change in height is what matters. It's not the absolute height because you as a physicist, like we've done before, get to decide what 0 is, right? So, let's say that I'm on that building again, right? I'm on that building. Most people, right, would say, let's set the ground as a height equals 0. because if I do that and drop a ball again, I want to know how high is that ball, right? So if that ball is, I don't know, 20 meters high, what's its gravitational potential energy? But it's what is the gravitational potential energy relative to where I care, right? So I'm setting the ground equal to 0. What if I had another building in the way? Maybe this building is 10 meters tall, and I want to know how much gravitational potential energy is. Well, I got to decide where I'm going to call 0. Is 0 the ground? Is 0, if I drop it, it hits the top of that building? So what matters when we look at things is how do things change? So if I'm going to say the ground is 0, gravitational potential energy equals mass times the acceleration of Earth's gravity times height. Let's just make this a 5 kilogram ball. So if that's the case, 5 kilograms times 10 newtons per kilogram times 20 meters above the ground. And so 20 times 10 is 200. 200, so 2 times 5 is 1,000. So then I get 1,000 Newton meters, which is an energy unit. So in SI units, that's 1,000 joules. All right, so that has 1,000 joules of energy compared to the ground. Well, what if I actually cared about compared to the top of this building that's 10 meters high? Well, maybe I set this equal to height equals 0, and then my new actual height is 10 meters. That would give me a different number, right? So what's going to end up happening as we go down this road is we're actually going to care about what the change is. We're not going to care about the absolute values. They don't mean much because you get to set 0 wherever you want. All right, so hopefully from this you see you can calculate the gravitational potential energy, but we're really interested in what the change will be when, say, we drop or throw a ball. So we'll be looking for that change and using that to our advantage. All right, I'll see you next time. The only way to learn physics is by doing physics. So here's a practice problem for you to work on. So we have this roller coaster, 1,000 kilograms in mass, that is at the top of a 100-meter hill. Now what I want you to do is compare how much gravitational energy that has, compare it to the ground, compare it to the top of the 80-meter loop, and compare it to the top of the next loop, which is 25 meters. So each time, compare it back to the starting position of 100 meters above the ground. Hit pause now so that you can solve this, and when you're ready to see the solutions, unpause the video. All right, so here are the solutions. So in each case, what we're looking at is we're solving for gravitational potential energy, which is the force due to gravity, which is mass times little g, which we'll use 10 in this example. And then it's the change in height. So when we look at the difference going from 100 meters at the top to the ground, which is defined as 0, well, the change in height is 100 meters. So 1,000 kilograms times 10 newtons per kilogram times 100 meters gives us 1,000,000 joules. And we do the same thing for the other two. So the top of the loop is only 20 meters different, right? So the top of the hill is 100 meters, the top of the loop is 80 meters. So all we care about is the change in this particular case. And so when we look at that, that's 20 meters, and that gives us a gravitational potential energy of 200,000 joules. Seems true with the top of the next hill. So if we compare 25 meters to 100 meters, then we have a difference of 75 meters. And so the change in energy, gravitational potential energy, is going to be 750,000 joules. So keep practicing and you'll get better.